So let's look at mobile SoC architecture. This is how the architecture of any mobile SoC would look like. This is not the exact architecture of A11. That's their proprietary, Apple's proprietary. But I'm here to explain in general how any mobile SoC would look like. Let's look at the details. It's pretty interesting. You take any SoC, there is a bus, it's called on-chip bus. So basically we connect all the IPs through this bus. Now this SoC is composed of various kinds of IPs. IP is nothing but intellectual property. So basically we define any complex hardware block as IP. So this chip is composed of various kinds of IPs. Now at the center, there is an engine. It does everything for the chip. So basically this engine processes the information. The chip is going to get all kinds of information from the external world, and the chip has to process the information and it has to produce the output back. So the chip needs a powerful engine. Now look at this engine at the center. It's composed of various kinds of IPs. There are different kinds of IPs. You need processors, different kinds of processors like graphic processors, processors like ARM cores, DSP cores, audio processors, video processors, security IPs, modem accelerators, JPEG accelerators. So the engine is composed of various kinds of processor IPs, and this engine is going to process all the information. Now, within chip, so basically we connect different kinds of interface IPs with processor. At the center, the engine is there. Basically, we have to connect different kinds of peripherals through interface IPs. Now, let's look at some of the interface units. For example, in case of mobile, basically we have to connect the SIM with the engine. So there is an interface called SIM, and there is a dedicated interface for camera unit. There is an interface for keypad, whether it's touch phone or the regular phone, you need keypad interface. And there is an interface for audio devices, and you may need interface like a mini USB. And there are some battery components like charger units, vibrators, and battery units, along with power management unit. And it has to be connected with the engine through interface IP. And there are other interface units like Bluetooth, wireless LAN, GPS, and they have to be connected with the engine through dedicated interface IPs. Also, you may need interfaces like TV out or memory interfaces. It has to be connected with the storage. The storage could be like NAND or NOR flash. This is how the engine will be connected with various interfaces. If you think of mobile, you may need all these kinds of interfaces. In general, if you look at the chip is composed of processor IPs and interface IPs, and there will be hundreds of IPs inside. That's why this kind of complex chip demands billions of transistors. Now, let's analyze this architecture with respect to low power design. Here, there are three major power domains: VDD1, VDD2, VDD3. The IPs which are highlighted in yellow color, they operate at voltage VDD1. The IPs which are highlighted in green color, they operate at voltage VDD2. The IPs which are highlighted in purple color, they operate at voltage VDD3. Why we do this? In CMOS, the power is directly proportional to the square of the voltage. So we try to control the voltage level. It's obvious that the entire chip is not going to operate at constant voltage level. Different blocks will operate at different voltage level. This is how basically we try to reduce the power consumption. So when it comes to doing this, what we do, we look at the activity of the block. If the IP is going to be high performance device, then we define voltage level accordingly. If the IP is going to be low performance device, then we try to reduce the voltage level. This is how we reduce the power consumption. There is another way. Look at here. There is a dedicated power management unit. Basically, it runs the chip on different power modes. For example, you are not watching the video. Then the video accelerator might not be active. The moment you watch video, then the power management unit will try to bring up the video accelerator. So it may want to restore the past information. That's what the power management unit does. It controls the entire chip on different modes, like the way you use laptop. If you look at your laptop, there are different modes like active mode, shutdown mode, hibernate mode. That's how the chip will also be run on different modes. Now, I want you to understand the design process, how these companies, product companies like Apple and Samsung, mobile companies, they design this kind of mobile SoCs. Let's look at this kind of SoC is pretty complex. So if you go to companies like Apple and Samsung, they don't try to design the entire chip on their own because they have to meet the time to market. Now you have to think about it. They always release the chips in every 6 months, and how they do it. So what they do is they always buy IPs from various IP vendors and they integrate all the IPs when it comes to this kind of SoC design. So they get a lot of advantages. One primary advantage is quality. Think about it. You need different kinds of components like Bluetooth, wireless, or different kinds of interfaces, different kinds of processors. So you need processor expert to design processor. You need Bluetooth expert to design Bluetooth. You need wireless expert to design wireless components. And you can't expect a person to have all these expertise. So what they do is they approach IP companies. They look at like, okay, you are the company which is specialized in processor design. This is the company which is specialized in Bluetooth. This is the company which is specialized in wireless. And they choose companies like this and then they buy IPs from these IP vendors. Now to integrate all these IPs, what they do is they decide on chip bus, and the bus protocol is primarily based on the processor. Now we are talking about Apple chips. What they might do is they might go ahead with a specific processor like ARM core. Let's say in this case they have decided to go ahead with ARM core, and ARM recommends certain protocols. There are different flavors like AXI, AHB, APB, and depends on the performance of the device. You can choose one of the flavors. So AXI is good for high performance device and AHB is good for low performance device. So we have to think of creating our own bridge. So in case of Apple, they create their own IPs. There are two IPs here. One is AXI to AHB. The other one is AHB to AXI. Or you can consider the two stuff as one IP and they can configure as they like. So this is Apple's IP, but they are going to buy ARM core from company called ARM, and they may need DSP core. So in that case, they might talk to multiple companies and then they might choose TI as their partner, or TI might be specialized in DSP design. So they might buy DSP core from TI, and they may need video accelerator. They might buy video accelerator from Samsung, though Samsung is their competitor, because Samsung is into all kinds of business, chip design and IP business. So they can buy IP from Samsung, and they may need some kind of audio mixer, and Sony is good in this field. So they might choose Sony as their partner, and they may need some security IP. EDA companies, they are good in providing various kinds of interface IPs and security IPs. Any kind of EDA company, Synopsys, Cadence, or Mentor, they might need some kind of graphics processor, and NVIDIA is good in this field, so they might choose NVIDIA. This is how basically they create the engine. The engine is composed of various kinds of processor IPs like ARM processor, DSP processor, graphics processor, security IP, audio mixer, video processors, right? And depends on the performance, they put different IPs on different buses. So here, ARM core and DSP processor and graphics processor, they are on AXI, and the other cores like video accelerators, audio mixers, and security IP, they are on AHB. In addition to this, they may need some interface IPs. You need to recollect the previous architecture. In addition to engine, we need various kinds of interface IPs. When it comes to USB, they may look at Cypress as their partner because Cypress is specialized in creating USB IP. and they may need camera IP to connect the engine with camera unit. So Sony is good at creating camera IP, and they may need some interface IPs like memory controller, I2S, SPI, UART to connect various things like Bluetooth or wireless LAN. And all these interface IPs are available in EDA companies. They can talk to any company like Synopsys, Cadence, or Mentor, and they can buy the design IPs from EDA. And in addition to this, they may need to design their own IPs. For example, they have to create IP to support their own interface, TV output. So in this case, this is going to be their own proprietary stuff. Similarly, audio output or LCD interface. So some of their IPs would be their own IPs. This is how basically they customize the chip and they differentiate their chip from the competitors. Think about it. You can't simply think of buying IPs from other vendors. If that is the case, anyone can create mobile SoC and there will not be any difference. And they may need some IPs, dedicated IPs for analog interface. And there are companies like Analog Devices. They are specialized in analog design. In addition to the on-chip components, you may need some external chips also. We can't integrate all kinds of IPs within chip. We have to think about various factors. How much it's going to be expensive. The more and more you try to include within chip, obviously the cost of fabrication is going to increase. So they have to take trade-off, quality versus cost. Obviously, you may get more quality within chip, but you have to think about the cost also. And in some cases, you may get these components as the chip, the external component from the vendor. So you might not be able to integrate everything as part of your chip. For example, you may need a Bluetooth component, you may need some storage devices. And if you are going to include the storage device within your chip, obviously the chip size is going to increase. You have to think about all these factors. So in addition to the chip, you may need additional chips like Bluetooth or storage memories or analog chips. So there will be additional chips on motherboard. But you can't think of having too many chips on board. That's where the SoC comes into picture. So basically, we try to realize the entire system on chip. That's why it's called system on chip. And this is how basically we design SoC. All right. We have been talking about iPhone chip. I want you to understand the history, the evolution of this chip. It started off with A4. It was based on 45 nanometer and the frequency was 1 gigahertz. And A5 based on 32 nanometer and the frequency was 1 gigahertz. A6, same 32 nanometer, 1.35. A7, 28 nanometer. A8, 20 nanometer. A9, 16 nanometer. Look at the frequency. Now it's more, 1.85. A10, 16 nanometer, and the frequency is 2.34. Now look at this A11, 10 nanometer, and the frequency is 2.39 gigahertz. These two things, the frequency and technology will always change. This is what I want you to understand from this evolution. A4 was based on 45 nanometer. Today, if you look at A11 is based on 10 nanometer. That is a huge difference. So we have to remember this Moore's law. The number of transistors in a chip doubles every 24 months. This is what Moore said. Why we do this? So basically, we always look at how to reduce the technology. If we can reduce the technology, then we can reduce the transistor size. What is technology? Technology is nothing but the size of the channel. The chip is made up of CMOS, complementary metal oxide semiconductor transistor. It has got source and drain. There is a gate in between source and drain. In VLSI, what we do, we try to change the channel size. So we reduce the channel size and the transistor size gets reduced. When we reduce the transistor size, basically we can think of packing more and more transistors into smaller and smaller chips. VLSI is a field which involves packing more and more transistors into smaller and smaller chips. That's what VLSI means. It's a field which involves packing more and more transistors into smaller and smaller chips. We can think of having billions of transistors per IC. A11 has got more than 4 billion transistors in it. Now, to realize this technology, we also expect a good progress in fabrication. You know, whatever the design you create, finally, the net list goes to foundry, and foundry is the manufacturing unit which fabricates the chip. So they should be able to upgrade their process. For example, you say like your design is based on 10 nanometer, the foundry should be able to support the same technology. Then only you would be able to realize powerful chip. So what we try to achieve, we dream of converting the complex PCBs into smaller chips. This is what we try to achieve in VLSI. This board is pretty complex. There are so many chips on it. Then we think like whether it can be converted into a single chip, something like this. ASIC and FPGA. In VLSI, there are two kinds of chips. One is ASIC, the other one is FPGA. Let's look at FPGA, Field Programmable Gate Array. It's a programmable chip. I would say a ready-made chip. We can buy this chip from the vendor. There are vendors like Xilinx and Altera, and you can create your own design. Later on, you can download your design into the chip. This is how it works. The chip is empty. You can download any kind of design. You can erase it. You can reprogram it. It's a programmable chip. So it's beautiful. You can do a lot of experiments. For example, while doing the design, something goes wrong, then you can erase the design, you can fix the bug, you can reprogram the chip. This is used primarily in defense sector because there we don't expect too much of customization. Also, FPGAs are good for certain applications like mathematical intensive calculations. You know, the companies like Xilinx and Altera, they also claim that they include a lot of macro cells or macro IPs as part of the chip, and they can do the mathematical intensive calculations efficiently, so you get more performance. When it comes to space-related applications, basically mathematical calculation is critical. That's where FPGAs have been used extensively. There are constraints. For example, you want to realize a complex chip like A11, FPGA might not be able to support because it doesn't have the enough space. You can think of realizing complex designs in terms of million gates, not in terms of billion gates. So obviously we need to think about ASIC. Look at ASIC, application-specific integrated circuit. Now, one requirement is very obvious. We want to customize the area and power. The chip doesn't have to be complex. Even it can be a very simple chip. For example, I want to design chip something similar to this button. I would like to have chip on my blazer. The chip should be able to get all the information, my body temperature, heartbeat, and it should be able to transfer the information to my mobile phone, and then mobile phone should be able to process the information. So here you look at this, the size is critical. At the same time, power consumption. If it consumes more power, obviously I need to think of including a battery unit. Then nobody's going to buy the phone. Even women can also think of having this kind of chip as earring. Then the chip should be able to generate power from the photons. Now there are some LED lights, they emit photons. It should be able to generate power from the photons. So here the power consumption is very critical. That's why if you look at the chips which have been used in toys, they consume very low power. Though they are not complex, still power consumption is critical. At the same time, when it comes to designing the complex chip like A11, multi-billion complex chip, then obviously we need to go for application-specific integrated circuit because the size is important. So when it comes to designing the mobile chips or iPod chips or iPad chips or the chips for the laptops, obviously we go for ASIC. And ASIC, there are some risk factors. ASIC respins, very expensive one. At the later stage, maybe during back-end flow, if you find any functional bugs, basically you have to start from the beginning. You have to look at like how this can be fixed at the architecture level. If you do some modifications in the architecture, you have to rewrite the code. You have to simulate it again. You have to synthesize it again. It's kind of iterative process, and that's going to consume a lot of time. So that's very expensive. That's why verification becomes critical for ASIC. After creating the architecture, you have to look at how best you can verify the source code. And we have to find the bugs as much as possible during simulation phase. If you leave any bugs, later on, it would be more expensive. That's called ASIC respin. So what we do is sometimes we think how we can use FPGAs to verify ASIC. Look at FPGA, the last one, FPGA prototyping for ASIC verification. Obviously, everyone goes for simulation. You have written the RTL code, and then now you need to write test bench. You have to generate stimulus. You have to verify the functionality. But the simulation is simulation. We don't gain much confidence. So what we do is we try to do this verification on the actual hardware. So we create the prototype for the chip. Now you think of A11. It's pretty complex, more than 4 billion transistors. So one FPGA might not be enough. We might need multiple FPGAs, like 10 FPGAs or 20 FPGAs. And then what we do is we partition the chip A11 into multiple major hardware blocks. And then we try to map each block onto each FPGA. Then we put all the FPGAs together on the board, and the entire board will be equivalent to A11 chip. This is called FPGA prototyping. Here, the only difference is it might not run at the same frequency. The frequency might be low, but still you can verify the functionality. So what I'm trying to do is I'm trying to generate a lot of real-time scenarios, and I'm trying to verify my design on the actual hardware. Even I would be able to connect a lot of peripherals, the real-time peripheral devices with my chip, and I would be able to do a lot of experiments. And this gives me confidence. I can fix bugs even in the software also. This is called FPGA prototyping. That's where FPGAs have been used extensively. All right. In this video, we discussed about VLSI, what is VLSI, and how we design powerful electronic devices like smartphone. We discussed pretty much about mobile SoC architecture, and then we discussed about Moore's law. We also discussed about FPGAs and ASIC. Hope you enjoyed this video. Thank you. Hi. In the last video, I have given a complete overview of VLSI. Now, in this video, I'm going to explain how we design any kind of chip. What are the various steps we follow as part of the design process? What is front end? What is back end? Let's look at the details. This is how the design flow would look like. It starts with the specification and ends with GDS2. Now, there are two major domains. If you look at this design process, specification to synthesis, it falls under front end, and the remaining steps which are related to P&R, they fall under back end. Now, let's look at every step in detail. I will walk you through all the steps. Specification. I want you to understand how we create this specification. Experienced engineers like me, engineers who have more than 20 to 30 years experience, we call them as architects. They define the specification. What they do is they interact with the marketing team. They collect all the details. So marketing folks, they always interact with the consumer. They try to find out what's their experience with respect to previous version, what kind of difficulties they faced, how they enjoyed the product, what are the good things, what are the things that need to be improved, and what are the various features that we need to include to compete with the competitors. So this is how the architects collect all the details from the marketing team, and then they look at the feasibility, like how many features, new features we can include, and how the new product is going to be. They visualize. Now let's look at how these architects define the specification. You take any electronic system, it's composed of both hardware and software. For example, iPhone. iPhone has both hardware and software. If you look at the hardware, there is a PCB inside, and the PCB has got a chip on it. It's called SoC. We discussed about A11. This is the main component of the iPhone. In addition to this, basically it needs some software. So here iOS acts like user interface. This is how we realize any kind of electronic system. So these architects take the system specification and they partition the specification into hardware and software, and they define hardware specification and software specification. We chip designers take the hardware specification and design the chip. In case of iPhone, it's going to be A11, and whatever the chip we design, finally it goes as part of the board. The chip will be on the board, and in parallel, the software programmers create the software, and finally they run software on the hardware, and then they try to verify the entire system. So it's called hardware software co-verification. Now, if you look at the hardware specification, we need to look at how much the chip is going to be complex. If it's going to be very complex, then we might want to go with ASIC, or if it's not very complex, then FPGA might do, or even in some cases, even standard chips might also do. This is how basically we approach. Now let's look at the ASIC. To design the chip, what are the important things that we need to look at? Specification is nothing but a document. It can be a PDF or it can be a Word document. Usually it's huge. There will be thousands of pages. Then you need to really understand how to approach this specification. So when it comes to specification, you have to look at certain important details like the interface, packet structure, and protocol. Let's look at the details. What is the interface? Interface is nothing but inputs and outputs. So to design any chip, you need to understand how many inputs, how many outputs, what kind of clock, what kind of reset, synchronous or asynchronous. And the packet structure. What is the size of the packet? What is payload? What is address? What is parity? What kind of parity? And how we can drive the packet to the chip. Because the chip is a digital component, it can understand only the binary. You can't drive any packet or frame. Then you have to convert the packet into binary. So are you going to drive something like bit per clock cycle or byte per clock cycle or more than 1 byte per clock cycle? That's what the protocol defines. So these are all the important things. In VLSI, protocol is very important. We always follow standard protocols like AHB, AXI, APB, SPI, UART. Now, when it comes to building complex SoCs, basically we connect various IPs. When it comes to connecting IPs, we follow the standard protocols. So you need to be good at certain protocols to get into VLSI industry. Now let's come back to the specification. Specification may have so much of information. There may be too many chapters, but you have to really look at the important details to start off with the design. And once you get into the implementation, then if there are any questions, any doubts, then you may want to refer a particular chapter to understand more. Now, you understood the functionality. It's time for you to create the architecture. It's time for you to create the architecture. Usually, experienced architects create the architecture. If you recollect, this is what we discussed during mobile SoC architecture. Basically, architecture is nothing but a block diagram. You can find all the details like how many IPs would be there and how all the IPs would be connected, something like on-chip bus. And the experienced architect will give the ownership of any particular IP or any particular subsystem to a technical lead. Then the technical lead will create the architecture something like this. For example, how the processor can be created. You might create architecture something like this. This might not be the exact architecture of ARM core, but this is how any microcontroller can be realized. It needs various kinds of components like arithmetic logic unit or decoders or registers. And then you may ask engineers like you to design a particular component. For example, you are new to the organization, then you might ask you like, hey, why don't you design the arithmetic logic unit? Then you might want to apply your digital knowledge and create the microarchitecture, something like this. Then there will be different engineers, they create different components, and finally the tech lead is going to put all the components together, and then he's going to create that particular subsystem. Then what happens? The architects create behavioral model. Okay, look at here. The design architecture is there. Now, to verify the functionality of the design, how the design is going to be, before getting into the implementation, I want to make sure that the design works fine with respect to functionality and performance. So, I'm going to create a functional model. It's called TLM, transaction level model. It's non-synthesizable. So here the goal is entirely different. When it comes to verifying the functionality, we are looking for more performance during simulation. We are not looking at synthesis aspects. Even after creating this model, we want to run even software and check how the whole thing is going to behave, the entire system, during simulation. So basically, we are trying to simulate the entire chip and check how the whole system is going to behave. For that, we create transaction level model. Why we call this as transaction level model? Everything is going to happen in terms of packets. The input will be packet, the output will be packet. Nothing is going to happen at the binary level. It's completely different from RTL. Then later on, obviously, the design team is going to create RTL. The RTL will have different kinds of goals related to synthesis. They might be looking at various things like area and clock frequency, and basically the design team uses languages like Verilog and VHDL. But if you look at TLM, the modeling engineers always use languages like System C, C++, and System Verilog, non-synthesizable model. And during verification, this TLM is going to act like golden reference model. So basically, the verification engineers will produce expected values for the design. To verify the design, what we need, the reference value. Look at here. Later on, the verification engineer is going to create the test bench, and the test bench will have components like scoreboard, and the scoreboard is going to collect the reference data from the TLM and the actual output from the DUT, and it's going to compare the design output with respect to expected value from TLM. This is how the verification is going to happen. So this reference model will be used at various stages. Now let's look at RTL coding. RTL is nothing but register transfer level. This is how the structure would look like. It has flip-flop, combinational logic, and flip-flop. And this is how the data flow happens, register to register. That's why it's called register transfer level. When it comes to synthesizable model, we look at two things: how much area it's going to consume, and how about the clock frequency, at what speed the design is going to operate. So to calculate the frequency comfortably, we follow this design structure. Look at here. So here, the clock period can be calculated using this equation. Clock to Q delay plus propagation delay of the combinational circuit plus setup time. So clock to Q delay of the first flip-flop plus propagation delay of the combinational circuit plus setup time of the second flip-flop. This is how we calculate the clock period. Once you know the clock period, then you can calculate the clock frequency. Clock frequency is nothing but 1 by clock period. We will discuss about the setup time and hold time. So basically, we follow setup time and hold time for the flip-flop. And for combinational logic, we have to calculate the propagation delay. Now, when it comes to design, basically, we look at like whether we can do everything comfortably within this clock period. You might come to know that the propagation delay is more. You have created the architecture, you have written the code, but during synthesis, you might come to know that this propagation delay is more. That's where you have to apply optimization technique. You have to minimize the logic. That's why you always go for K-map techniques. This is something about RTL. Now let's look at the coding. Basically, we use HDL to write the source code. There are two main languages we use. One is Verilog, the other one is VHDL. Both the languages are equally powerful. You can use any one of the language. When it comes to writing synthesizable model, two things are important. Always remember. One is synthesizable subset. The other one is coding style. What is synthesizable subset? The language is huge. You cannot use all the constructs for the design. There are certain constructs, they are non-synthesizable. They are meant for verification. For example, in Verilog, we don't use initial for design. It's meant for test bench. Or while loop is non-synthesizable, or we don't use any delays. So you need to understand which one is synthesizable, which one is non-synthesizable. Also, while writing the source code, you have to think about it, how the source code is going to be EDA independent. You can use any kind of tools. There are different EDA companies like Synopsys, Cadence, and Mentor, and your source code should be able to work fine with any kind of tool. That's what you really need to understand as a good designer. As a good designer, you need to understand how to write EDA independent RTL code. The other thing is coding style. You want to implement a sequential logic, something like flip-flop, or you need to use passage clock in the sensitivity list. Or you want to implement multiplexer, it should be a parallel logic, so you have to use case. Or you want to use prioritized logic, something like priority encoder, then you may want to consider if-else. So different logics demand different kind of coding style. You need to understand both synthesizable subset and coding style. Okay, now you have written the RTL code. It's time for you to verify the functionality. Whatever you have implemented as part of the design, whether it works as per the specification, you have to prove the functionality. For that, you need to write another program called test bench, and the test bench generates stimulus. It drives the stimulus to the design. When the design produces output, basically it compares the design output with expected values. This is how the simulation happens. Verification also happens at different level, block level, subsystem level, and chip level. So you need to understand how to approach different kinds of verification. For example, block level, we always apply white box verification. We have to verify everything thoroughly. So we need to look at what's happening really to the internals. We need to look at all the internal components and analyze. That's called white box verification. When it comes to chip level, basically we follow black box verification because the chip uses the pre-verified blocks. So we don't really need to verify each and everything inside the chip. So we are going to look at only the inputs and output. We apply stimulus and then we look at the output and how the transformation is going to happen between input and output. That's how we look at full chip level verification. And we follow certain process. Before writing the test bench, we create a detailed plan, what kind of stimulus we want to generate, and how we are going to track the simulation with the help of coverage. There are different kinds of coverage like code coverage and functional coverage. And how to create test bench, something like this, the architecture of the test bench. Everything will be captured as part of this plan. It's called verification planning. And what kind of strategy, white box or black box or gray box. And based on the plan, we run simulation and eventually we look at the coverage and sign up the simulation. If the coverage is going to be 100%, we are fine with the simulation output, we sign up the simulation. That's how verification happens. If you look at the simulation environment, it would look like this. You have to deal with source code and you have to live with waveform. You have to analyze it all the times. Debugging is the major part. And you need to look at the coverage progress. You have to look at the output status. This is how the environment would look like. And these are all some of the tools. We call them as verification platforms from various EDA companies. We have verified the functionality. If there are any bugs, then we may need to go back to RTL and we have to rewrite the source code to fix the bug. And after fixing the bug, we have to rerun the simulation. So this is kind of iterative process. You have written the RTL code, you have run the simulation, you identified the bug, you fixed the bug, rerun the simulation, and everything is going fine, then you move on with synthesis. Let's look at synthesis. So basically, you have written the RTL code. The source code is there, Verilog code, and you synthesize it. Eventually, it will be converted into netlist. Here, you look at the difference. This is RTL, and after synthesis, it becomes like netlist. So when I say netlist, it will have only the primitives, the gates. The entire design will be realized in terms of gates. So we have this big question: how many universal gate we need to realize the IP or chip? Whatever we design the chip, we need to understand like how many universal gates we need, either NAND or NOR. So basically, there are two kinds of chips we create: NAND based and NOR based. Mostly we go with NAND because it consumes less power. That's why if you look at digital, there are two ways. One is SOP, the other one is POS. Some of products which is meant for NAND based, and POS which is meant for NOR based. So basically we go with positive logic and define the functionality, and we apply SOP and we create a NAND based chip. And you can always convert SOP into POS or POS back into SOP. That's mainly for converting NAND based into NOR based or NOR based back into NAND based, right? This I explained very well. This I explained in detail as part of digital module. Now let's look at the synthesis. So basically synthesis converts RTL code into netlist because we want to know how many gates we need. And during synthesis, we should be able to estimate the area, estimate the frequency. It won't be the exact value because still we don't know much about the interconnections, the actual placement. So it will be the estimate. Even if we don't get the actual frequency here, we have to apply the constraint. So basically the tool is going to optimize the design. Internally it will apply K-map techniques and it will try to optimize the logic. That's how we try to increase the clock frequency. So what happens during synthesis? It converts the RTL code into netlist. Synthesis is over. Now we have the netlist. We need to verify the functionality of the netlist. It's called gate level simulation. There are two ways. You can use equivalence checkers to verify the functionality, or you can run even simulation. Look at this. This is RTL. You have the netlist. This is implemented in terms of flip-flops and combinational logic. And if you look at this, is implemented in terms of gates. Everything is in terms of gates, including the flip-flop. Now we have to make sure that the functionality remains same, because sometimes there may be some issue, there may be some bug in synthesizer. Then instead of producing the equivalent logic, probably it might introduce some kind of error. So we have to cross-check with the help of equivalence checker. So in this case, equivalence checker is another tool. We feed RTL and the netlist to the tool. The tool is going to read both, and eventually it will convert everything into Boolean equations, and then it will try to compare the equations. If it finds any mismatch anywhere, then it will highlight. This is called equivalence checking. Then there is another way. It's called simulation, gate level simulation. Whatever the test bench you have used for the RTL, you can also reuse the same test bench. You have to write test bench in such a way that you can reuse it. Instead of RTL here, you have to instantiate the netlist, and then you need to run the simulation. But the important point is you have to verify the functionality of the design again after synthesis, because there may be some issues in synthesizer. So we want to make sure that the same functionality is retained even in the netlist. All right, we are fine with simulation. Now we have to look at DFT insertion. So this is called design for test logic. There are various things like stuck at 0, stuck at 1 faults. You need to really understand how we model all the faults. This is part of DFT, right? But I want you to understand the logic. Like, so basically during DFT insertion, what we do is we try to replace the existing flip-flop by scan flip-flops. So this scan flip-flop would look like this. It will have a multiplexer at the input. The multiplexer will have two input. One is the normal data input, the other one is scan input, and it will also have scan enable. And why we do this? Why we replace the regular flip-flop by scan flip-flop? Look at here. This is how the RTL would look like. Okay. Now we replace the flip-flop by scan flip-flop. So every scan flip-flop has multiplexer at the input. Okay. Now I can operate the entire chip on two modes. One is the normal mode, the other one is test mode. So here you look at this. This is normal mode, this is test mode. Now I am showing you the normal mode. How the data flow happens. The data goes to flip-flop, combinational logic, and flip-flop. So it's called RTL, register to register. The data flow happens. But during test mode, this is called scan chain. I want to skip the combinational logic and I want to connect all the flip-flops like shift register. So what I'm going to do is, during test mode, I'm going to inject the stream of bits, and then I'm going to check whether the same stream of bits come through output. If it happens, there are no short circuits within chip. This is very useful later on to find out whether there are any fabrication faults within chip. This is what actually DFT does. Then we look at various things like stuck at 0 faults, stuck at 1 faults, to identify whether there are any short circuits or open circuits within chip. This is called DFT insertion. So what we do is, after synthesis, we take the netlist and we replace the regular flip-flops by scan flip-flops. That's what DFT does. Okay, all right. Now the front-end design is over. We started up with the specification, and then we synthesized the RTL. We created the netlist, and later on we inserted the DFT logic. Now the final netlist is ready for P and R. That's what verified during DRC. Finally, we go for layout versus schematic. So whatever the final routed netlist, physical netlist that you got from P and R, let's look at floor planning and placement. In backend, what we do, basically we create the floor plan. We really need to decide how the chip is going to be, whether the chip is going to be like square type or rectangular type. And based on the shape, we need to decide how the lower level components can be placed efficiently. And while placing the component, we have to think about the routing possibilities also, how easily we can make the connection. This is how basically we plan the floor planning. Floor planning is very critical. So while doing this floor planning, we have to think like how efficiently we can utilize the space. And the placement decides how the routing is going to be without any congestion. Then after placement, we do clock tree synthesis. By default, the clocks will be connected with various flip-flops like this. Here you look at. The clock is connected with this flip-flop. The same clock is connected with other flip-flops. So here, the wire length is different. The clock will reach flip-flop 1 faster than flip-flop 2. Right? So there is an issue called clock skew. Now look at this. Within chip, there may be millions of flip-flops, and if the clock is going to be connected like this, then the clock will reach different flip-flops at different time, and there will be clock skew issue. So the expectation is the clock should reach all the flip-flops at the same time. So for that, what we do is we follow various kinds of methods like H3. You look at this. The source is going to be like this, and the clock source will be connected with this clock tree. And here the flip-flops will be connected at the edge. So here there are 4 flip-flops, here there are 4 flip-flops, here there are 4, here there are 4. So totally 16 flip-flops you can connect with the clock source like this. Here if you calculate the wire length, it will be same. Also, we insert buffers like this. Then only the clock will be distributed properly. Otherwise, the clock strength will also vary. Right. So during clock tree synthesis, we look at like how to remove the clock skew and how to insert the clock buffers so that you can take care of the clock distribution. Right. So that's called clock tree synthesis. Then we take it through routing. Routing is all about making the connections. We have placed all the components within the chip. We have done clock tree synthesis. Now we have to make the connections. So while making the connections, basically we need to take care. There should not be any short circuit. There should not be any congestion. We might want to rearrange certain placements to take care of the routing. Okay, now we have made the connections. It's time for us to verify the timing. So this process is called static timing analysis. During synthesis, we also verified timing, but it was not the actual frequency. But now we have done the routing. We have come to know about the actual wire length. And this is the right time for us to verify the actual timing, whether the chip is going to work at the expected frequency. That's what we are trying to verify. Now, you need to recollect the basics. This is RTL. Register, combinational logic, and register. This is how the data flow happens, register to register. Now for flip-flop, basically we have to follow setup time and hold time. If you want to register any data into flip-flop, you have to take care of setup time and hold time. So here the data is stable during setup time and hold time, so data will be registered. But here you look at during this window, setup time and hold time, the data is changing. So there is setup time violation. During setup time, the data is changing. Here, there is hold time violation. There may be different violations like this, and there may be millions of flip-flops, and we cannot do this manually. That's where we apply static timing analysis. It's a tool, static timing analyzer. The tool is going to check whether there are any setup time violation, whether there are any hold time violations at every node within the chip. That's how we try to verify timing. And eventually, we make sure that the equation works fine for all the flip-flops at all levels. If there are hundreds of levels within chip, for every level, like register to register, this equation will be applied and all the parameters will be applied, and it will calculate like, okay, this is the clock period that works fine for all the flip-flops, all the levels. And based on this clock period, the tool can confirm this is the frequency. This is the maximum possible speed. So if there are any variations with respect to timing, then we might want to go back to placement. We have to rearrange the cells. We have to redo the clock tree synthesis, and we have to redo the routing and then take care of the timing. Still, we are not able to meet the timing. Then we have to go all the way back to architecture, and we need to make the changes primarily at the architecture level. Then everything has to be repeated. It's going to be very expensive. This is called respin. We have to really avoid this. Now it's time for us to create the physical layout. So this is how we try to realize the actual implementation on the silicon. So this is how we create the layout. We call this as stick diagram. And after creating the actual layout, we go for physical verification. There are two things we do. One is design rule check. The other one is LVS, layout versus schematic verification. So design rule check, we take the stick diagram, we look at like whether we follow the fabrication standard. For example, we want to realize the chip for a particular technology, let's say 12 nanometer. Then the fabrication defines certain standards for 12 nanometer. This is how basically we have to create the layout. So here the space between the metal layers in terms of lambda or the width of the metal layer. Everything is defined by the foundry, and the tool is going to apply these parameters, and the tool is going to check whether the complete layout follows the fabrication standards, and that's what verified during DRC. Finally, we go for layout versus schematic. So whatever the final routed netlist, physical netlist that you got from P and R, basically you have to once again verify with respect to schematic, the original netlist. Once again, we apply equivalence checking. The tool is going to compare the functionality of the layout with schematic. It makes sure that the functionality is retained in the routed netlist. And then finally, we release GDS2 to Foundry. We discussed about the complete design flow. It started off with specification and it ends with GDS2. Specification to synthesis, it falls under front end, and the remaining steps, they fall under back end. We started off with spec, and based on the functionality, we created the architecture. And based on the architecture, we created the behavioral model. Basically, we use behavioral model to generate the expected values for verification. And based on the architecture, we create RTL coding. RTL means register transfer level coding. It's a synthesizable model. We use HDL to create RTL, and then we simulate the RTL and verify the functionality. For that, we write test bench. And after verifying the functionality, we synthesize the RTL and generate netlist. After generating the netlist, we insert the DFT logic in the netlist. So basically, we replace the regular flip-flops by scan flip-flops. And then the netlist goes to P&R. We do floor planning based on the shape of the chip. We decide how the components can be placed efficiently. So after doing the placement, we do clock tree synthesis. There mainly we look at how to avoid the clock skew. And then we do the routing, we make the connection. After making the connection only, we will come to know the wire delay. So we go for static timing analysis. We make sure that the timing is perfect. So to put it in simple way, what I would say is, in front end, we verify the functionality. In back end, we verify the timing. Always remember this. Because to verify timing, we need the actual layout. That's what happens in the back end. And then we create the physical layout, how the actual chip is going to be. We call this as stick diagram, how the transistors can be realized on actual silicon. So we create the layout, and then we apply DRC to check whether the physical layout follows the fabrication standards. And then finally, we take the layout and compare it with the schematic, whether the routed netlist retains the same functionality. And after the physical verification, we release the netlist GDS2 to Foundry. This is how the design flow works.